Hello everyone, today we're going to start a new topic on thermal physics, all about what we mean by temperature, so chapter 14 and then 14.1. We'll mention about thermal equilibrium. There's something called an absolute scale of temperature. We'll then start looking at the difference between Celsius and something that you may or may not have heard of, which is called Kelvin, and then we'll be converting between degrees Celsius and Kelvin as a unit for temperature. So as part of the objectives today, something that we need to make sure we can absolutely do is draw a model of solids, liquids and gas. Now, this is something that you should have been able to do from primary school maybe, certainly Key Stage 3 when you joined, but something that people in Year 13 still can't do. We'll then, as I said a second ago, look at temperature and then something called heat, and then the difference between the two. Reminder about particle theory and then relating that to temperature. And then something that you'll need to go away and do a bit more about is the laws of thermodynamics. So to start us off, get yourself a scrap piece of paper, draw 3 boxes like I have done, label them solid, liquids and gas, and then give it a go. Draw, using the particle model, what you can recall from probably GCSE, but what does a solid look like? So draw some circles. What does a liquid look like? And what does a gas look like? And when you're ready, press pause and then press play again once you are done. No cheating. Give it a go. Okay, hopefully you've given that some time. So solid. Now the trick here is not to make the circles too small so that they fit. So a solid is regular structure, all compacted, no spaces. Now I've rushed this a little bit. We shouldn't have any crossovers. They should be perfectly formed spheres. Just imagine snooker balls just stacked on top of each other. I'm going to do gas next because that's the thing that most people can also do. So a gas, same idea, but with lots of gaps. Now some of you might have done little marks to suggest that they're moving, or arrows. That's equally fine, but likewise solids are also vibrating on a fixed spot as well. But what about liquids? Now something that most people do with a liquid is this. Is this you? Have you just drawn another gas, but one that's maybe slightly more dense? Because that most definitely is not a liquid. So I'm going to rub that one out and we'll give it another go. So a liquid has to be pretty much a solid, but just with a few gaps. Every single circle has to be touching another. And again, like with the solids, there should be no overlaps just there. But what we've got is a series of spaces, but every single one somehow is linked to another one. So a liquid is pretty much like a solid with a few gaps in. Another thing to remember about a liquid is it fills the container, so always start at the bottom and move up when drawing them. But this is a skill you absolutely have to do, and a skill that people do, in particular liquid, struggle with. So again, another question for you, or 2 questions. What do we mean by temperature, and what do we mean by heat? We use temperature and heat quite a lot, but what do we mean by them? So again, in a minute, press pause, and then once you've had a thought, maybe done some research, then press play again to see what we should be writing. So hopefully you've given that a go, and let's go through the answers. So what do we mean by temperature? Well, it's how hot or cold something is. So the hotter the object is, the higher its temperature will be. And we will use some kind of thermometer to measure the temperature of something that's on a fixed scale, so 0 to 100 if it's Celsius, and then we can have a comparison between 2 objects. But heat, that's how much energy is involved. So normally for temperature, we will use degrees C, or in a minute Kelvin, and energy is all about joules and thermal energy. Now what we know is if we have 2 objects, A and B, if this one's 30 degrees and this one's 10 degrees, if there's a difference in temperature, we know the direction of heat flow or energy flow. We know that the temperature will go down from the 30 and go up from the 10 because there's a movement of energy. So something with a different temperature tells us which direction energy will flow. And then eventually they'll be the same temperature. So if we imagine a hot cup of tea, leave it out, it's going to be the same as the surroundings. And at the point when the tea is at the same temperature as the room, that's when you're in thermal equilibrium. Both are in the same temperature and there's no movement of energy from one to the other. So that's thermal equilibrium. So this leads us on to the laws of thermodynamics. Now I've written the 3 laws quite glibly here. It's up to you to go away and read about them in a little bit more detail. But the first one is the conservation of energy. So energy cannot be created or destroyed, just transferred from one form into another of sorts. Number 2, it's all about entropy, and that can never decrease over time. So at this point you might want to go and find out a little bit more about what's meant by entropy. And again, it mentions entropy in the 3rd law. So entropy approaches a constant value as temperature approaches absolute zero. So we'll see a bit more about this as the course progresses, but certainly spend 5-10 minutes just looking at the 3 laws. Now there is actually a 4th law, and most people would say it's the most important law. It came after the first 3, and because it's seen as the most important, it was called the Zeroth Law, so that it goes before 1, 2 and 3. What it states is if 2 thermodynamic systems are each in thermal equilibrium with the third, then they are in thermal equilibrium with each other. In your book, in chapter 14.1, figure 2, it has this picture. And if we just focus on just A and B to start with, if they're in thermal equilibrium, they're the same temperature, then no energy gets transferred between the 2. If we take B again, but put it next to another object, C, and again, they're the same temperature, there's going to be no transfer of thermal energy. But then if we move A and C together, because A and B are the same as B and C, then by logic, A and C must also be in equilibrium, and that's what the Zeroth Law is talking about. If A and B are the same, B and C are the same, then A and C must also be the same. Now I've mentioned kelvins a few times, and in the previous chapter that we've looked at as well, kelvins was mentioned, and there's this thing called absolute zero. So absolute zero is at 0 Kelvin. So at 0 Kelvin, we say that that's the coldest that you can get. You can't get any colder or cooler than 0 Kelvin. It's when everything has no internal energy. And to translate that into what we're more used to, degrees Celsius, 0 Kelvin is the same as minus 273 degrees C. The other thing to point out is if you go from 2 to 3 degrees C, that interval of 1 degree is the same as the interval going from 2 to 3 Kelvin. The gap between the numbers is equal to each other, they just start at different points. So, given that knowledge, how many kelvins is equivalent to 100 degrees Celsius? So have a think, and when you're ready, press play. So hopefully you've given that one a go. So this is the equation that links everything together. If you want to find the temperature in Kelvin, all you've got to do is find out what it is in degrees C and add 273 to it. So if we wanted to find out how many Kelvin 100 degrees C is, it's 373 Kelvin. So feel free to use this as an equation if you then need to find out how many degrees something is, so it'd just be Kelvin minus 273. So in the book it goes through it in a bit more detail. Figure 3 in chapter 14.1 gives you a bit more of an indication than I've done in this video. So at this point let's just talk a bit more about what the Celsius scale is all about. And it's the one that's most commonly used and has been around since around 1742, but it's based around 2 fixed points, 2 fixed known points. So there's our thermometer, and at the bottom our fixed point, quite arbitrary, 0 degrees C. So someone said that, okay, freezing point of water is at 0 degrees C, therefore that's what it is. And then the next arbitrary point was just chosen to be 100, and that was then assigned the fixed point of the boiling point of water. So that was then divided into 100 equal spacings, quite arbitrary, and that's how we have our 0 to 100 degree scale for Celsius. So it's based around our two fixed points. So if we now compare this a little bit more to Kelvin, so what happened here is, rather than starting or stopping at 0 degrees C, the scale was then extended to the coldest possible temperature you can get to, and that was worked out at minus 273 degrees C, and then that was given the term 0 Kelvin. And then because each interval has the same value, going back to the previous page when you saw the equation, then 0 degrees C is 273 Kelvin, and 100 degrees C is 373 Kelvin. And that's our absolute temperature scale. So for homework, give these questions a go, the summary questions from your book. I think the answers should be in the back, but any problems, please let me know.